Thanks. Okay, let us start. As you probably know, that the magnetic force microscopy is a part of atomic force microscopy, and in generally the goal of magnetic force microscopy is to image magnetic states of different magnetic materials and samples and devices. I spent several decades working in magnetism, including magnetic force microscopy and magnetic dynamic microscopy, but today I will be talking mainly on standard application of magnetic force microscopy, and we will learn different techniques, the advantages and disadvantages of this technique, and we will see different examples of applications. So coming to basics. As you see in this slide, to make a magnetic force microscopy, you need standard atomic force microscope, and you need a magnetic sample. And what is important, you have magnetic probe. Usually, a probe is standard atomic force probe covered by magnetic materials. And due to dipole interaction between magnetic sample and the probe, the probe it changed its frequency, resonance frequency. So you can see here that the probe is driven by additional generator, the additional force to the resonance condition, and of course, due to interaction between sample and the probe, these resonance conditions can be changed, and depending on whether you have attraction or repulsion, the changes goes in different directions. So in principle, due to these changes, the amplitude of precession due to off-resonance conditions is also changing, but it is much more convenient to measure not the amplitude of the oscillations, but its phase. And as you see in this slide, on two examples, for attractive and repulsive interactions, the phase is changing in opposite directions in both cases if you stay on in the given frequency, and in such a way one can distinguish between repulsive and attractive forces. In many cases, it's rather important. Of course, as a part or branch of atomic force microscopy, magnetic force microscopy has different advantages and disadvantages. The first is the most important challenge of this technique is that since magnetic probe you use is also its magnetic moment, it creates dipole fields which can, in principle, disturb magnetic sample. So it's important to understand that when you make a magnetic force microscopy, you should take care not to disturb this magnetic state which is you have without your probe. The second point is, and the second point that you can also not only disturb the state, you can easily remagnetize the probe by the sample. By the sample by the probe. In some cases disadvantage, but in some cases it's real advantage. And we will see today later that in this way you can make magnetic nanolithography. And the last but not least is that the dipole fields you use are non-local. It means that the resolution, lateral resolution of magnetic force microscopy is not so good as atomic force microscopy. It's because contrary to atomic forces which are local, magnetic force microscopy is not local, and therefore the resolution which you can obtain by magnetic force microscopy cannot be so good as atomic force, like atomic resolution. But nevertheless, as we will see, that this resolution can be in tens nanometer regime. However, this non-locality gives you opportunity to see below the surface. So if you have multi-layers, and due to non-local nature of the dipole fields, you can observe not only magnetic properties of the upper layer, but also layers behind the upper layers, and this is in many cases a big advantage for your measurements. So here you see several examples of magnetic force images in different magnetic structures. On the left, you see the standard image which people very often use to calibrate their devices and to show that to find the resolution. You see a magnetic structure of a hard disk drive. And you see that the resolution of this image is rather good. It's definitely below 100 nanometers, and but one should notice that this is rather simple test. Since the magnetic material of hard disk drive is very hard, you have no problem with disturbance. You can use probes with high magnetic moment materials like cobalt, and you can also have high thickness of the coating, and it means that you have very good very high noise to signal to noise ratio, and you can reach very good resolution. Another picture on the slides are a little bit more challenging. You see, for example, several pictures of here and here. You have several pictures of magnetic garnet. These magnetic garnet are very magnetically soft, and therefore it is very easy to disturb their magnetic structure just by a probe, and therefore in order to reduce the disturbance, sample with the thin magnetic coating were used, and therefore the magnetic disturbance fields on these garnets has been minimized. Finally, on the right side here, you see domain structure of cobalt gold multi-layer structure, and again, to obtain small disturbance, the tip was covered by magnetic materials with low magnetic moment, and this is again a challenge because this is reduce your signal, and you have it's challenging with respect to the signal to noise ratio. Okay, here we have another example of MFM application where a single ferrochrome particle has been images using MFM. And this example shows you possibility to analyze MFM images quantitatively. You see on the upper row of the pictures is experimentally measured images, and one sees that for the same particles you have different magnetic states, and these different magnetic states are can be easily detected by magnetic force microscopy. Here in the middle, you see the corresponding simulated images of MFM, which correspond to different magnetic structures as shown on the bottom. And you see that magnetic force microscopy images directly connected with the structures, and using these structures you can identify these structures using these images, but also you can take quantitative information about these states. For example, you can determine the size of the core if it's necessary, and you can also, if it's necessary, you can also obtain the size of the H domains on such a ferromagnetic particle if necessary. Our next example is connected with investigation of multilayers. As I already said, that due to non-locality of magnetic fields, dipole fields which you are sensitive to, you can investigate the magnetic properties of the layers, not on the surface layers, but on the buried layers which is shown here. You see here the stack consists of 3 layers, and depending on realization, the chirality of this stack can be either right or left. And this chirality is definitely determined not the properties by the top layer, but by the properties of the both bottom layers. And you can see on this image that it is easily to distinguish between right and left chirality, and in such a way you can determine the properties of the layers which are on the bottom. Okay. Our next example is connected with non-engineering of magnetic states. It is now very hot topic to produce a given structure of magnetic states, for example, defined magnetic domain structures. And a simple, straightforward way to create such magnetic states is first to create, using, for example, electron beam lithography, different shapes of magnetic ferromagnets. And here you see on these images, this image and these images, electron microscopy images of such nano elements. And correspondingly, magnetic MFM images are shown here and here. And you see, by changing the shape of the electric ferromagnetic elements created by electron by focus ion beam or electron beam lithography, you can really create different magnetic states. For example, you can create either vortex or anti-vortex in such structures. You can also perform measurements at different temperatures using MFM, and in such a way you can create, you can investigate phase transition. Here is an example of the phase transition where the magnetic anisotropy is changed with the temperature. You see you see topography and magnetic MFM images of the same sample at different temperatures, and it is clear that with the topography nothing happens dramatically, but domain structure changing really dramatically. And by analyzing these domain structures, one can clearly see that changes of the magnetocrystalline anisotropy. You see uniaxial anisotropy, easy cone anisotropy, or easy plate anisotropy. So such an example shows you that MFM is also a very powerful tool for investigation of magnetic phase transition. Very important feature of MFM images is a magnetic field. Since applied external magnetic field can change the magnetic state of the sample, it is very useful to be able to investigate, to obtain MFM images by applying magnetic field. Here is example shows you the structure of so-called artificial spin eyes, which is nothing else as artificially prepared honeycomb structure of magnetic dipoles. In this case, these are magnetic iron bars with micrometer or sub-micrometer sizes. And you can see that without magnetic field, the structure is rather chaotic. You see different orientation of these bars, but applying even rather weak magnetic field, you can order these elements and create real order structure. Of course, since you have almost mesoscopic, not magnetic moments, mesoscopic moments, so you need rather weak magnetic field to create order. For samples where the magnetism is determined by atomic moments, where the magnetic moments is much smaller, you definitely need much higher fields, and in this sense it is also rather important to be able to apply high magnetic fields during your measurements. Another example of rather weak of the images obtained by a rather weak magnetic field is presented here on the bottom, and again these are a Garnet field. And it is well known that in Garnet field, domain structure is rather complicated due to rather complex interplay between dipole fields and in these domains. And since Garnet fields are low coercivity fields, so the domain structure is also due to this properties, the domain structures are also quite complex. You see that how this domain structure is changing, is evolving when you apply magnetic field, and even rather weak magnetic field gives you already a quite ordered structure of the domains. It is always useful to have a possibility not only applied magnetic field in plane, as we have seen in previous examples, but also out of plane. And here you see magnetic domain structures of also Garnet field implied perpendicular out of plane magnetic field. And you see that contrary to the pictures we have seen before, applying perpendicular field, you do not order domains. You change the domain structure, but ordering is not seen here, and it is clear why, because the in-plane magnetic field breaks the symmetry, in-plane symmetry, and it is not surprising that domains in previous slide were oriented correspondingly. The out-of-plane magnetic field doesn't change. Doesn't break the symmetry. Therefore, changes of the domain are seen, but they are still symmetric with respect to rotation in plane. So, in this sense, there are several possibilities to create, to obtain such images. And what is important from the technical point of view, since you are working with magnetic fields, your device should be extremely non-magnetic, because all possible stray fields of the magnetic parts of the devices can disturb your measurements. Therefore, it is important to develop measuring heads which are purely non-magnetic. And it's also important to develop powerful magnets and for application of external magnetic field both in plane and out of plane orientation of the field. From the technical point of view, it is also rather important to have high quality of the cantilever you use as a probe. And it is since the quality of the cantilever is determined by the ratio of losses and energy pumped by generator to the cantilever, it is always good to reduce the losses. And an obvious way to reduce losses of your cantilever is to reduce viscous losses due to just air. So as you see in this graph, if you reduce the ambient pressure, if you reduce the pressure, you dramatically reduce the losses of your cantilever, and then in such a way you dramatically increase by a factor of tenths or even more the quality factor of cantilever and sensitivity, because the quality factor determines you the line width of your resonance, and sensitivity, derivative of the line width, which determine you the phase shift and therefore the sensitivity of your images. So as it demonstrated in these pictures, the increase of the Q factor really improve the signal to noise ratio, and this is clearly seen in this picture. What is important to note is that you don't really need very high vacuum. So you see even by 0.1 torr, you already almost on saturation, because at such pressure the losses determined by the air are comparable with internal losses of the cantilever itself. Therefore, it's not really necessary to have high vacuum from this point of view. However, as we will see later, for some applications, really high vacuum is necessary for MFM images. So here it's shown the device from NT-MDT, which allows you to create low vacuum, which is enough to improve the signal, to improve the K factor of the cantilever, and to improve the signal-to-noise ratio with respect to ambient conditions. Moreover, using additional gases, one can also create environment which is important for different applications, for example, for biological application or for some chemical application, you can use different gases. What is, however, important that if one needs to investigate samples at low temperatures, you need to have high vacuum, because otherwise, even by this low vacuum, the moisture which you definitely have in your system will disturb your interface surface of your sample, and definitely disturb the signal which you obtain from MFM. To avoid that, it is necessary to use high vacuum device, and at pressure below in the regime of 10 to minus 8 torr, the moisture or growth of ice on the surface of your sample is not so important, so you can work several tens of minutes up to 1 hour without disturbance of the interface. So you see here an example of measurements at low and at room and low temperatures, and you see clearly difference between two pictures measured at room temperature and low temperature, and there are two contributions to this difference. First, this contribution is obvious, is as we already discussed, that working in high vacuum you increase the Q factor of your cantilever, and therefore the signal to noise ratio is improved. The second physical region for difference in these two images is properties of sample, which is investigated here. Here you see that this is a multi-layer, and the magnetic part of this multi-layer is cobalt, very low cobalt, very thin cobalt film. And its properties strongly depends on the temperature, for example, domain size, and another to determine this. And this is also connected. These changes of these properties also contribute to the changes between these two images. What very important thing in application of magnetic force microscopy is magnetic nanolithography. As I said, since the magnetic probe, magnetic tip, has its own magnetic moment, its influence your sample investigate. In some cases, it's a disadvantage, but in many cases, it is advantage because we can use it as a nanolithographer. Here you see an example of such application. You have arrays of cobalt platinum disks, and here on the top you see the just image, non-magnetic image of these disks, and by putting a magnetic tip close to one or another tip, you can change the magnetic state of this disk as it's shown in this cartoon. And it can be really realized as shown by this real image. So you see that one or second or three, even more disks are remagnetized, and in general it can be used for magnetic storage. Recent development of magnetic storage industry is so-called pattern media, where the information will be stored using one element, such similar disk, and the problem how to address this information in such pattern media is very challenging task, and magnetic force microscopy can definitely contribute to this development. Another example, also very similar, of the similar application is given here. You have here array of images of cobalt dots. These, by the way, are dots which we have already seen in the beginning of our webinar. But now, instead of investigation their magnetic states, we can just change the states. And you see here, you see that on the left of the picture, you see these dots which are magnetized just by external magnetic field of 1 Tesla. And after that, using the magnetic tip, you can change the magnetic states of these dots in rather either locally. You see here that single dots can be remagnetized, or even on the area, a large area, and in such a way you can make magnetic nanolithography. As you see in the previous slide, quite strong magnetic fields are necessary in many cases. And therefore, I'd like to say a few words about recent development of NT-MDT, where device or were set up for applying rather strong magnetic field what has been developed, because I was one of the co-authors of this device, so I'd like to say a few words about that. So usually it is rather big challenge to create strong magnetic field, both out of plane and in plane, and the difficulties are obvious since you have to just because of geometry, you cannot create standard pole, standard system, magnetic system with two poles with a small spacer between them, because you need the upper hemisphere of your devices for the MFM head. So you have only possibility to put your magnet on the bottom of your sample. And for this geometry, it is very difficult to create a strong magnetic field. Nevertheless, we were successful in creating magnetic magnet, permanent magnet, important to say, which can provide magnetic field up to 1 Tesla, demonstrated, and up to 0.8 Tesla is already developed device. And in these cases, the magnetic field is concentrated in a rather small area to increase the magnetic field. And but since we work with microscopy, this concentration is not so important on the scale of the MFM images. This field is still rather homogeneous. Advantage of permanent magnet is clearly you don't need a cooling. The temperature is standard, which is important for stability. There is no extra vibration, and this newly developed model is compatible with existing IFM system from an integral family. Here is shown the vertical component of the magnetic field as a function of radius, with the distance from the center of the magnet, and for a vertical distance. You see that magnetic field is really strongly concentrated in the close to the surface and in the middle, in the center of the magnet. But as you see, the scale here is microscopic. The scale here is millimeters. So for small elements, which are usually used for MFM, this field is rather homogeneous. And it's also rather easy to change this magnetic field either by mechanical motion of some parts of the magnet, or if it's too complex for some measurements, by just changing the position of the sample. So as it's shown here, by changing the altitude of the samples with respect to the magnet, which you can do using just different non-magnetic space, you can easily change magnetic field from 1 Tesla down. What is also interesting that just due to Maxwell equation, as soon as you have non-homogeneous component of field, Z component, you should also have another component of the magnetic field, and it's shown here where the in-plane component of the magnetic field in the same device measured is shown. So it is clear that in the center of the samples here, this in-plane magnetic field is 0. So you have pure conditions of out-of-plane measurements, or measurements with out-of-plane field. But if you move your sample from the center of the magnet along the radius, you can reach a area where the vertical field goes to 0, and horizontal field, in-plane magnetic field, has its maximum, and as you can see, this maximum is quite impressive. So it's 0.6 Tesla, 6,000 kilograms. So in this, in one device, one has both out of plane, strong out of plane and in plane magnetic field, which is very important in many applications. So another important feature is high resolution. As I said, that the magnetic force microscopy cannot obtain the resolution which people obtain using atomic force microscopy. But nevertheless, as there are several approaches which allows you to produce rather high resolution. For that purposes, one should use special probes, high resolution magnet probes. And as you can see here, that these cantilevers have different properties, but they can create really very good resolution down to 10 nanometers resolution, and which is rather important. They are quite stable, which is also a problem by magnetic force microscopy, that the probes goes broke. Okay. So here is different realization of the techniques I has already mentioned. So here company NT-MDT has two different platforms, which is one is Integra platform, which has much more possibilities for application, and the Solver platform, which is more for development for beginners, which is simply easy to use and easy to educate your people. Okay, thank you very much for your attention. And if you have questions, you can send these questions to the webinar NT-MDT. Excuse me. You should, sorry. Yeah, it's webinar at nt-mdt.com, and I will be happy to answer your questions. And also there is a possibility to ask the question in the chat. Thank you very much. Okay, I have already some questions here, and okay, here there was a questions. How can attractive and repulsive forces be differentiated in the images? What is the significance of color? Well, you see, if you look into this image, it shows you resonance, black curve shows you resonance curve without any interaction. If you have attraction, your resonant frequency goes in one direction, and is shown here by blue curve. If you have repulsion, your frequency goes in other direction, as it's shown as a red curve. And by just staying on this given frequency, without interaction, the phase between measured oscillation of the cantilever and driving force of your generator will be 90 degrees, as it usually the resonance condition. If you're out of resonance conditions, as it's shown by red and blue curve, you have either increase of the angle or decrease of the angle, and in such a way it is easily to distinguish between repulsive and attractive interaction. Very, very good questions I have. Once the external magnetic field realign the magnetic field of the tip. It is it's very important questions, and of course, if you have strong magnetic field, you should use probes which are either have a rather strong coercivity, for something like cobalt chrome probes, cobalt platinum coating, or if you said, okay, if my magnetic field realign magnetization of the probe, it's again well-defined magnetization. So as soon as you know the magnetization of your probe, you can again clearly understand your images. So this is the issue which you take care, but it can be easily done. Okay, we will see what is it. Well, there are some technical questions. For example, what kind of pumps usually used? Well, it depends on what vacuum you want. If you want to have just a low vacuum, it's a standard rotating pumps can be used. If you need high vacuum, it's turbomolecular pumps are standard good solution. Although if it's necessary, you can use another types of pumps like cryo pumps and different. So it is just depending on your application. Okay, I see that we have many technical questions, and we will be asking these technical questions. Will be answered in the written way. Somebody asking about data recovery from the broken hard disk. Sorry, I'm not expert in hard disk. Yeah, there is a question, is it possible to measure magnetic moment or magnetization? Well, of course, the example of quantitative MFM images shows you that you can determine the magnetization of your sample by simple comparison of simulated MFM images and measured images. For that, you need to calibrate your device. For that, you need some reference samples. So after measuring, once measured your reference sample, you can calibrate your device or your probe in terms of magnetic fields, and then you can quantitatively measure the magnetization of the sample. The question is, what is the weight and dimension of permanent magnet? Well, as I said, there is a standard device which already ready to be bought. The diameter is 40 millimeters, and the width is the thickness is 12 millimeters, and the weight is about 100 grams. I have a question about in-plane magnetized tips. Well, it's also a rather interesting question because, of course, the sensitivity to the magnetic field you have strongly depend on the magnetization of the probe. And usually, people use vertically magnetized tips because it's just more stable from the shape I know. However, using, as I said, using coating with high coercive materials, you can pre-magnetize your tip horizontally, and then you will be sensitive to different components of the magnetic fields, and some features which are not shown by vertically magnetized tips can be measured using horizontally magnetized tips. There is also a question about the permanent magnets. How can one calibrate the magnetic field? Well, because this field is rather inhomogeneous. As I said, these inhomogeneity are macroscopical. So if you look into the pictures, I have shown that the changes of the magnetic fields happens on the scale of millimeters. So since it's permanent magnet, and if you take care about this magnet, not hitting it too much, not letting falling down, these magnetic fields is stable. Once calibrated, once measured, you can be sure that the magnetic field is well known. There's again a question whether it's possible to apply magnetic field on the heating. Well, in general, it's strong challenge, because the permanent magnets which usually used, they survive up to 100 C. So if you're talking about heating of 20, 30 C or above the ambient temperature, just up to 60 degree, or 80 degree, these magnets can be easily used. Above 100 degree, it's a big problem, and of course, you cannot get such a strong magnetic field as for by ambient temperature. Well, the question is also about presentation, that how the images are obtained after nanolithography. Well, as I said, when you create the magnetic images, you have a given distance between magnetic probe and your sample. And therefore, this distance gives you possibility not to remagnetize your sample when you make images. So the very important parameter is the distance between the probe and the sample. So by putting your probe immediately close to the sample, you can make lithography, but measuring on some elevation, which is several tenths of nanometers, you can so strongly reuse the tip fields, so you can measure without lithography. Well, there is a questions about some kind of literature and documents, books. We will create some database on some information which is available, and this information will be sent to the customer, and if you ask. There is also a question about interplay between characteristic of the material covering the probe and material you investigate. Of course, there is interplay, so one should be careful about that. But it's rather it's not so straightforward. Therefore, I cannot answer this question directly. So if you send more details about your problem, about your challenge, we can definitely find an appropriate solution. I'm also asked about any application on MFM in food sample, biological samples, or metrics. Well, magnetic biology is now is a very hot topic now. As you probably know, there is so-called giant magnetoresistive effect, which is allows you to determine very tiny magnetic field. And now the development goes in some aspect of biological studies to put nanomagnets on the biological elements like cells, to put nanoelements and detect these cells by detecting the magnetic field of this nanoelements. So I'm not aware on MFM images on such elements, but I'm sure that development goes in that direction, that earlier or later such images will appear. Well, it was a question about standard resolution one can achieve in ambient temperature and pressure. And the question whether it's possible to have 1 to 5 nanometer literally. No, it's impossible. Without any precaution, you can easily obtain a resolution of below 100 nanometer, 50 nanometer probably. But anything below you should be given by special application. Well, the question is, do you need special probes for vacuum measurements, or are the standard probes are appropriate? As far as I understand, you don't need the special probes for vacuum measurements. You just use the standard, and you increase the quality of your picture with the same probe just for free, just by pumping your system out. The question is, what is vertical resolution on MFM? Well, in this, it's difficult to discuss this, the MFM imaging in these terms, because you measure not the topography, you measure magnetic field at some level. But what is possible to ask, for example, what is the maximum depth of magnetic layer you can identify it. Again, this is everything in up to order of between 10 and 100 nanometer, which is determined by the size of your problem. So if you have lateral sizes of 100 nanometers, for example, then the changes of the dipole fields in vertical direction will be also order of these 100 nanometers. If you have very tiny structures of 20 nanometers, the changes in vertical direction will be also order of 20 nanometers. Should you have very large structures like 1 micrometer, so the depth sensitivity will be also very, very large. As I said, I have rather quite a lot of technical questions about alignment, about application of different particular devices. I will ask the technical staff of the company to answer these technical questions. Well, the question is rather interesting. What will be the resolution under magnetic field? Well, in principle, the application of the magnetic field does not change your resolution, because excuse me, resolution is mainly determined by the properties of the probe, for example, its curvature and the value of the magnetic moment on the probe. In this sense, I would say that it's not changing. However, I can imagine that by applying by measurements in strong magnetic field, you can get better resolution and by measuring in zero magnetic field, because as soon as you apply strong magnetic field, you should not take care on possible remagnetization of your state using by the dipole fields of the probe. So you can really use probes with thick coating and high magnetic moment materials. Now, I was asked what magnetic moments can be measured using using MFM. What is the sensitivity with the standard tips and ambient conditions? Well, to be honest, I'm not ready now to answer this question. I need to make some estimation, and definitely this question will be answered in a written way. Again, I have a question about the distinguishing between between attractive and repulsive forces. As I said, it's rather simple. As you see here, you need just to measure the angle between the phase between the reference signal driving force and oscillation of your cantilever, and if this angle is less or more than 90 degrees, you have the attractive or repulsive force, provided, of course, that your tip is magnetized as shown in the picture. Should the tip magnetize in opposite direction, the contrast is also will be reversed. Okay, I think that I have answered most of the physical questions, and all other questions will be answered, which are mainly technical, will be answered in a written way by the company NT-MDT with interaction with my corporation. Thank you very much for your attention, and have a good day.